Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas?
Why do some things glow in the dark?
Why do animals not understand humans? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Chris Smith. Now, Mike says at the beginning of the year he flew back from Singapore on the A380 jet, biggest plane in the world. How big can we go with planes, he asks. Have we reached the limit, or do you think planes will get bigger?
Well, the physics of flying remains the same whether or not you're making a paper aeroplane, to a certain extent, or you're making a massive aeroplane. And in fact, bigger aeroplanes are quite good because the really big ones, which take off, go high, fly for a long way, and then come down, they're actually very efficient. And if you talk to people in the know, they'll tell you that some of these big aeroplanes are doing about the same amount of fuel efficiency in terms of how far they're getting a person per mile, in terms of how much fuel they're burning, as something like a Toyota Prius. So they're actually very efficient. But it's the taking off and going down again which makes them inefficient. So when you have a very big aeroplane that you're using on short journeys, that's a very bad way to fly. If you're using a very big aeroplane, lifting a lot of weight and going a very long way, that's a very efficient way to fly. In terms of actually whether or not it's worth getting them any bigger, well, that's a different question, because obviously we have to bear in mind that flying is encouraging people to produce greenhouse gases and inject various particulates and aerosols high up in the atmosphere where they could be harmful to the environment. And for this reason, it's a question of whether we want to encourage people to fly that much or not, and whether or not the kind of routes that are going to be operated by these very big jets are actually therefore going to make them a better option for the simple reason that I've outlined, that they can take more people further and stay airborne for longer. And this means they're actually going to end up being more efficient in the long run. So I think it's more than just the physics. It's more a sort of environmental argument as well, because you're going to have more noise, you're going to burn more fuel, you're going to have more manufacturing costs, and so on. So I think it's not a question of whether we could. I think it's more a question of whether we should. And I think we have to talk to someone in the industry to give us a proper answer to that question. But the bottom line is I don't think there's really any reason why you couldn't use the same physics, as long as the materials can hold up, to build bigger and bigger aeroplanes. It's coming down to the materials in the end, because you need something which is capable of remaining strong and rigid. And as you scale things up, the forces become bigger and bigger and bigger, and you need to make sure you've got materials and structures that can accommodate that. I fully expect that we could produce materials that could accommodate around that. Whether it would be efficient, though, different story.
OK, thank you very much, Dr. Chris. Now, Nigel says, hello. Over the years, I have experienced what I can only describe as tiny electrical shocks in bony parts of me in reaction to some external stimulus, such as at the craft fair when my arm, when using a wooden pendulum that gyrated over hidden samples of water, several metals and especially gold, in his forehead, between his eyes when looking at my wife's left temple across a large room full of noisy people, which she reacted to, and from cranium to heels and back again when walking inwards across the ditch circle at Stonehenge and in other places too. The closest I can get to it, says Nigel, is a description of goosebumps or along some specific tracks. I'm fascinated to know if there's any possible explanation. Maybe he thinks he should try divining rods at some time. What do you reckon, Chris?
It could be just that this is some kind of neurological thing. Sometimes, in some people, and I'm one of them, when something makes you jump or something unexpected happens, you can get occasionally little muscle tweaks or twinges and spasms. And, for instance, when I was doing some histology work, I was cutting very thin sections of tissue in a laboratory, and you cut this section and it would be literally a few thousandth of a millimetre thick, and you'd have to pick this tiny section of tissue up with a paintbrush and then laboriously, gently lay it on a glass slide. And occasionally you go to pick it up with a paintbrush and it would drop. And when it dropped, then I would jump, and my chin, or one muscle in the middle of my chin, probably my mentalis muscle, would give a little involuntary jerk. And you think, oh, what's that? And it was reproducible. I could keep doing this. If ever I kept unexpectedly dropping a section, then it would make this muscle go. And I think that possibly this is something similar, where when something unexpected happens to Nigel, or when something makes him jump or get excited, then perhaps he gets these little muscle spasms. It's a bit like when your eye twitches sometimes. I wonder if that's what he's describing. I haven't come across it, though, in any other respect, so that's pure speculation. So if anyone has any suggestions, do let me know.
Yeah, do share your twitches with us, please. Now, Jackie's also sent an email in and says, hello to both of you. What is your thinking about the evolution of dogs? Having recently looked at an old book, given that in the past canine experts looked on the ancestry as being wolfish and zoologists had other ideas, what do you think, Dr. Chris?
Well, dogs are entirely a product of human intervention. We know that because we've genetically sequenced them. And what genetic sequencing of dogs reveals is that they are all related, they are all derived from the same ancestry as wolves, and they are the product of selective breeding purely by humans. And they are therefore only thousands of years old dogs. They didn't exist. If you go back more than 5,000-10,000 years ago, you will not find dogs. They're entirely a product of human activity. And basically what people did was to select the wolves that were the more friendly ones that would approach people, and they brought them closer to humans. These dogs then, or wolves as they were then, were selectively bred to be the more friendly ones, the ones that were more obedient, the ones that would actually make good friends to humans, because of course the reason we wanted to domesticate these animals was because they could do things we couldn't. They've got incredibly sensitive noses, so they could smell things, they could find food, they could find water, they could smell danger. They have incredibly developed senses of hearing, so they could hear things that we couldn't much sooner than we could. So an approaching enemy, an approaching creature that might cause harm to us, they could pick that up very, very quickly. So therefore they were a very good companion to have, and of course they had a bark. So as soon as something bad was going to happen, they would let us know. They made great guard dogs. For that reason, mankind wanted to bring them into the fold. So as we slowly domesticated these animals, they then began to be bred even more selectively to try to rear groups of dogs that were even more specialised for doing certain things. And that's how we ended up with all the different breeds that you see. They're purely mankind's work of selective breeding, mixing certain combinations of genes or DNA together in order to get the kind of outcome that you want. So you find a dog which you know is very good at swimming because you want a dog that will go into rivers and retrieve something for you. You find a dog which has got nice long legs, making it good at jumping over obstacles. You find a dog that's very good as a companion, or very good as a guard dog, very vicious, for example. And you breed those traits, and that's exactly what happened.
All right, well, Jackie also asks that she says she likes to read old and new books, and also given the importance of tropical rainforests, Dr. Chris, what is your opinion on the destruction of all the old trees in this country? Some of them have gone without fair means as well. Jackie, thanks for your question. What do you say, Chris?
What I say is that, in fact, probably combating the Spanish Armada and all the naval battles we had to participate in over the course of the history of the country, and also making iron, was responsible for getting rid of a lot more trees than we do these days. Most mature trees have got tree preservation orders slapped on them, and also people are much more conscious these days of the environment around us and how long these trees take to grow. If you look in the countryside and you see a big old horse chestnut tree, it's probably 300 years old. If it's too big for you to get your arms around the base, then it's probably a lot older than you are. And these trees take a long time to mature. The country used to be covered in them. And when we decided to up our population, to build boats and also to build houses, we began to cut them down. And basically that's been going on for quite a few thousand years in this country. A couple of thousand years since the 1,000 years or so since the Anglo-Saxons cleared a lot of the land to build farms and things. But certainly this was a much greener country than it now is, and it was mainly green because of big trees. Where we really need to worry, though, is where there's a lot of very big trees, and that's in the Amazon, because the Amazon is a massive, massive sink for carbon. In other words, this huge tract of rainforest is drawing down, locking away tons and tons of carbon every single year from the atmosphere. So it's helping to offset us driving to work, us lighting oil fires or heating and boilers and things to keep our houses warm. the Amazon is helping to compensate against that. And if we're not careful and we lose it, then we'll obviously be in a position where we don't have that safety net. So it's very important to preserve that, and that's going at an incredible rate. I don't have the numbers at the front of my mind, but we know that areas the sizes of whole countries are disappearing from the Amazon every single year. So it's very important that we come up with a strategy to stop that happening. The reason it's happening is because people need to live. The people who live there need to rear animals so that they can grow crops and feed themselves and make some money. And that means we have to find a way of helping them to be more sustainable in their activities. We can't just ban them from doing it because they've got every much as right to eat and drink and try and be happy as we have, but we need to find a way to help them to do that more with nature than by destroying the Amazon rainforest, because if we let it go too far, you just don't get that rainforest back. Because if you ask ecologists, they'll tell you that even if you leave the land after it's been cleared, it will take probably 100 years before it comes back to being proper rainforest again. That is, if the ground ever recovers, because it very quickly gets eroded. So I wouldn't worry so much about the trees in this country, which I think we're better at looking after. I'm more worried about the trees in areas in the third world where there are no preservation systems and where people are desperate and tend to clear the land just to survive.
All right, well, caller this time, John in Peterborough. His question is, when there's been a lorry crash or a diesel spillage, it's announced that the road has to be resurfaced. Could you tell us why this is, please, Dr. Chris?
Well, the thing is that whenever you get lots and lots of an oil-based substance spilled on the road is, and this is concrete, very often contains large amounts of tar, bitumen, and oil is a very good solvent. So if you've got a stain on something, I can remember myself, I had an oil-based stain on something. If you wanted to get it off, petrol was a brilliant way to do that. Diesel is a brilliant solvent because it's a mixture of hydrocarbons, short chains of carbon atoms, which are very good at working their way in amongst oily substances and plucking out some of the chemicals in those substances and dissolving them. And so as a result, if you've got a tarmac-based road, bitumen, and you put lots of oil onto it, then that oil, in sufficient quantities, can begin to dissolve some of the road surface. It will leach into the road surface as well. And this is risky for a number of reasons. One, it can obviously destabilise the surface. But two, it can continue to leach out of the surface subsequently again. And as a result, the surface can become very slippery for prolonged periods, which is dangerous. So that's why I think they tend to, especially if there's been a fire as well, because that can do the same thing, can obviously damage the fabric of the road. So if in these circumstances, the safest way to resolve the problem is sometimes to literally rip up that bit of road and relay it.
Two questions coming up. One about what a cloud's made up of, and also about a tyre. Is the piece of tyre touching the ground, standing still constantly once a vehicle is going along, no matter how fast it's going? From Alan. If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. It's Dr. Chris of The Naked Scientist here. Dr. Chris, our question from Doris in Great Yarmouth. What are clouds made up of?
Well, clouds are principally water. And what happens is that energy from the sun, heat, lands on the Earth. Roughly every square metre of the Earth's surface is hit by energy from the sun at the rate of about 1 kilowatt. So 1,000 joules per second are hitting the surface of the Earth. The energy is soaked up by the surface and in some cases passes into water. So if obviously it hits the ocean surface, it warms the water. This enables water molecules to have enough energy to break away from each other and to become airborne, so they evaporate. The water molecules then stay in the air, and because warm air rises, the warm air, because it's less dense, goes upwards in the air. And as it goes upwards, of course, two things happen. One is that it feels less pressure from the atmosphere as it rises, and when you have less pressure on something, it expands. But when something expands, it also gets colder. So as the air rises, it gets bigger, it gets colder, and colder air cannot carry as much water as warm air can. And so what happens is that the water molecules, which are in this evaporating, in this rising damp air, the water molecules begin to coalesce. They group together and form little droplets. And they tend to do that around something called a nucleation site. So it's very difficult for individual water molecules to stick together in the first place. But if there's a tiny something there already for them to form around, they like that, and it facilitates the process. So you get these little specks of usually dust, sometimes ice crystals that are already there. Even dandruff has been found in clouds, but also bacteria. There's a certain type of cloud-riding bacteria called Pseudomonas syringae, and these bacteria use clouds as a means of dispersal. They get blown off of plants up into the sky, and they land up in the clouds, and they have on their surface a certain combination of chemicals which are aligned in just the right way so that water molecules stick onto them and stick onto them in just the right configuration to form ice crystals. So these bacteria then encourage a hailstone to form around them. That encourages the cloud to later rain down, bringing the bacteria back down to Earth, but hundreds of miles away from where they started. And they then land on a plant, and they invade that plant, take up some nutrients from the plant, they grow, they increase their numbers, replicate themselves, and then they get blown up in the air again and go onto another cloud. So clouds are basically ice crystals, water, which is condensed around tiny structures, nucleation sites, and they form those big puffy clouds because basically they're frozen. And depending upon how much water they carry, they are either a darker colour, or if they're very thin and wispy, they don't have much water, they're a lighter colour. And that's why big black storm clouds are the colour they are, because they're so dense, because they've got so much water in them, and they just want to rain it all down.
We don't want any of those, particularly over this weekend anyway. But now, Chris, Alan in Orpington says, can you clear something up for him? Someone said to him once that when a vehicle is going along, no matter how fast the vehicle is going, the bit of tyre touching the ground is standing still. It's constant. Is this true? Chris?
Hello, Alan. Very good, interesting, very good question. I think what that person was getting at is that in order for the car to go along, the car has to be accelerated by the tyres having friction with the road. So in other words, the car is going to feel a force because of air resistance when it's going along, which is what stops it continuing to accelerate. And that air resistance must be compensated by the engine putting more effort into pushing the car along. In other words, it's got to transmit that momentum, that force, through the tyres and onto the road surface. So at any given instant, one component of the tyre must be gripping on the road. There must be friction occurring between the tyre and the road to push the car forward. So if you were to freeze the car at any given moment, then yes, some part of the tyre surface has to be effectively pushing against the road, but obviously the wheel is turning as a whole, and obviously if it didn't, the car wouldn't go along. But the evidence that the friction is not perfect is that tyres wear out, and we know that across the world millions of tons of rubber is rubbed off of tyres on roads all around the world every year. And that's because when the tyre goes round, it doesn't make a perfect contact with the road, it does slip a tiny bit. And when it slips a tiny bit, you're losing some rubber particles every time the tyre goes round, and that's why tyres wear down. If that wasn't happening, they'd last forever, but they don't, because there's a little tiny bit of rubber being rubbed off with every revolution.
OK, well, interesting stuff. Jenna has said a bit of a weird question, Chris, but watching Star Trek, and in this they transport people, could this ever be possible?
I'd love to think that it would. I can remember, as probably many people can, watching Star Trek when I was little and being absolutely gobsmacked that they could have these fantastic things that are a bit like sort of communicators, where they're like a mobile phone, and you whip open this thing like a mobile phone on the surface of this planet, and you can say hello and have a conversation with someone. And who would have thought that could happen? But, you know, it wasn't many years later, we have mobile phones and everyone just dials people up. What about the internet? You know, people thought, how could we possibly connect all these computers, millions of computers together around the world, and have everything that pretty much we ever knew accessible from a home computer, which is basically what the internet is. That there are resources on the internet, pretty much the sum total of mankind's knowledge is on there, and you can get to it. I mean, that too was an amazing kind of, wow, how the hell could we ever have seen that coming? And that's why the guy that helped to make it possible became Sir Tim Berners-Lee. He got a knighthood for doing it. Some people say he maybe should get a Nobel Prize too for what he's done. But the point is that at the moment we think that teleportation of a whole person is probably out of the question, but I don't want to become a stick in the mud here and say, no, that's not going to happen, because I've seen it happen with the other technologies on Star Trek. Even the doors that open automatically. I mean, they're kind of commonplace now, aren't they? But they were really cool on the first Enterprise. These doors that open when people came along. Yeah. And so I think it'll probably be a very long time. We can't even teleport anything other than a tiny particle or photon at the moment. So actually being able to teleport a person with millions and millions and millions of atoms in a person, and you've got to rearrange or take that configuration, move it to another site, and then rearrange all those same clusters of atoms in exactly the same places. It's unfeasibly complicated and probably not possible, certainly at the moment. Maybe in the long run, though, perhaps it could be.
All right, well, you never know, do you, in our world of science as well. We've got one or two bits and pieces here. Now, Mike has said that how do the gas lighters work that you light the oven with? He's just got a thing that you just click and it all happens. So how does that actually work?
There are two ways that those lighters work. The handheld ones are usually what's called a piezoelectric lighter. What this is it takes advantage of the piezoelectric effect. This is P-I-E-Z-O, or if you use it to light a pizza oven, you could call it a piezoelectric effect. But basically what this is there are certain kinds of crystals that when you apply pressure to them, squeeze them, they liberate an electric charge. So in the handheld gas lighter, it produces that flurry of sparks by squashing a crystal and tapping off the charge, the electrons that are freed up by that, and then passing them around a circuit whereby they have to jump across a small gap in that circuit in order to complete the circuit, and that makes the spark. That's one way of doing it. Another way of doing it is to use a coil. And what you do is have, say, a battery connected to a coil with lots and lots and lots and lots of windings on it. And you have two coils. You have a primary coil with a few windings and a secondary coil with lots and lots and lots and lots of windings. And you press a button in and release it. And what this does is allow a current to flow through the first coil, which makes a magnetic field. And this induces current via a magnetic field in the second coil. You then release the button, and this collapses the current in the first coil, collapsing the magnetic field, and this causes a very dramatic change in that magnetic field, and this induces a very big a very big voltage in the second coil, which has got lots of windings, and that then is passed around a circuit in the same way. So there's two ways of doing it, one of them much more portable than the other, so it depends on whether you've got something rigged into your oven or whether you want to have something portable, which of those two you use.
Eileen has got a good question. I think this has been on everybody's mind. When we lose weight, with that successful diet or cutting down our eating, where on earth does it go?
Well, you breathe it out. When you lose weight, you're burning off fat, largely. Fat's the body's energy store. And fat is hydrocarbons. It's the same stuff, actually, that runs cars. It's oil. And this is a very efficient energy. It's made of lots of carbon atoms linked together, surrounded by hydrogen atoms. And your body can burn those, and what it does is it takes little chunks of those fats and breaks them down into carbon units and then oxidizes them. And carbon plus oxygen equals CO2. So when you burn fat, mostly the product is carbon dioxide. There are some other metabolites as well. You can make some other things called ketone bodies, but principally... and glycerol and alcohol, but principally the product is carbon dioxide. That's where they all end up eventually. So basically, by doing exercise and things and eating less than you're burning off, you're basically turning your metabolism into reverse. Instead of laying down fat, you're burning it off, and as a result, it's turning it into CO2, carbon dioxide, which you breathe out.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.